Welcome guys to the third video on solution of differential equation using Laplace transformation. Alright, so we've already done 2 videos ahead, so do well to watch the 2 videos for proper understanding, especially the first video which I did on this topic. I gave all the key shortcuts which are going to be employing to solving any problems involving differential equations and Laplace transformation. Alright, so let's consider this question on the board. The equation says solve the differential equation 3x dot minus 6x equals sine 2t. Given t equals to 0 and x equal to 1. All right, so this is our given initial condition. Now, the equation is simply 3x dot minus 6x equals sine 2t. Mind you, when you see x dot in calculus or differential equation, x dot simply means the x all over the t. That's what it means. Okay, so if you see x dot dot, it simply means the squared x all over the t squared. All right, so in this case, just keep it in mind that this x dot simply means the x all over the t. So rearranging this equation now for clearer understanding, this becomes 3 the x all over the t minus 6x, and this is equal to sine 2t. All right, so that is the equation. We are to find the general solution using Laplace transformation. All right, so I highlighted in the first video that we have 4 steps to solving differential equations using Laplace transformation. The very first step is simply obtain the Laplace transformation of all the given functions involved in the equation. So we are to write this equation or rewrite the equation in terms of Laplace transformation. So we are to now write the Laplace transformation of 3 the x all over the t, okay, minus Laplace transformation of 6x, and this is equal to the Laplace transformation of sine 2t. You have this. Okay, so if we write this, of course, let's bring out all the constant out of the Laplace sign. So bringing out 3, we have 3 Laplace of the x all over the t minus, also bring out 6. We have 6 Laplace of x, and this is equal to Laplace of sine 2t. We have this. So we now need to write all the Laplace of these variables or these functions. And in the first video, I explained that the shortcut is this. The Laplace of the x all over the t is considered to be s bar minus s naught. Always keep this in mind. Again, the Laplace of s itself is considered to be what? X bar. And then now we have the Laplace of sine 2t. We did this now in the table of standard values. That's the very first video we did. First 3 videos we did on Laplace transformation, talking about introduction of Laplace transformation involving table of constant or standard values. So do well to watch that video for proper understanding. But I explained that in that video, if I'm asked to find the Laplace of sine at, then from the table of standard values, this is equal to a all over x squared plus a all squared, where a is a number attached in front of a trig function. So we did all of this in that video. Do well to go and watch the video for proper understanding. So this is just a standard value that you must know. It's a standard value you have to know, which you're not expected under this condition to start solving the Laplace of sine 2t. You are supposed to have known the values at its standard conditions. All right, so Laplace of sine 2t automatically now becomes what? Remember a, and a is a number 2, so it becomes 2 all over x squared plus a squared, which is 2 squared, and 2 squared becomes what? 4. Hence, Laplace of sine 2t is simply 2 all over x squared plus 4. Okay. Now, having written the Laplace transformation of each of the variables, let's now plug them back into the equation. This is what we are solving with now. So we have Laplace, we have 3 times Laplace of the x over the t, and we know the Laplace of the x over the t to be this. This becomes 3 times s bar minus s naught, okay, minus 6 times Laplace of x, as can be seen here, and Laplace of x is simply what? X bar. So this is minus 6 x bar, and this is equal to Laplace of sine 2t and that gives us 2 all over x squared. This is 2 over x squared plus 4. You have this. All right, so let's expand the bracket. We can continue that here. So 3 times this gives us 3s bar minus 3s naught, okay, minus 6s bar, and that's equal to 2 all over x squared plus 4. All right. Now, the next condition says, or the third condition for solving differential equations using Laplace transformation, the third condition says, insert the given initial conditions. Now, in the equation you're given, when t equals 0, okay, x equal to 1. And I said that the initial condition is such that when t is equal to 0, x is always taken as x naught. And in the equation, they say x is equal to 1, so which means x naught is equal to 1. Hence, wherever you see x naught here, put in the value as 1. So this becomes 3s x bar minus, I have here 3x naught, and x naught is 1. This becomes 3 times 1, okay, minus 6x bar minus 6x bar, and this is equal to 2 all over x squared plus 4. You have this. Okay, so this is now 3s bar minus 3 times 1 remains 3 minus 6x bar equals 2 all over x squared plus 4. All right, so the third condition says rearrange the equation to obtain the Laplace transformation of the solution. So we are now to rearrange the equation to obtain the Laplace transformation of the solution. And the Laplace transformation of the solution is simply what? X bar. So we have to what? Rearrange x bar, keeping them on one side, and make x bar subject of the formula. So let's rearrange now. I have 3x bar here, 3s bar. Let's also bring this one close, minus 6x bar, minus 6x bar, okay, minus 3, and this is equal to 2 all over x squared plus 4. Okay, so if we continue, let's now factor. X bar is common between these two. We have x bar into 3x minus 6, okay, minus 3, which is equal to 2 all over x squared plus 4. Now, we need to make x bar subject. That is what the law is saying, or the condition is saying. Now, let's make x bar subject. That means we have to, first of all, you send minus 3 over to this side of the equation. So I have x bar. So I have x bar into 3s minus 6 equals 2 all over x squared plus 4 plus 3. Okay, so if negative 3 cross over and equal to, and it becomes positive, so you have this. Now, to make x bar subject, it means we divide both sides by what? 3x minus 6. So this simply implies that x bar is equal to 2 all over x squared plus 4 divided by 3s minus 6 plus 3 all over 3s minus 6. So we have something like this. Now, the fourth and the final law says at this point, you take the Laplace inverse of all the functions. So we find the Laplace inverse of x bar, and this is equal to the Laplace inverse of the individual term that makes up x bar, which is 2 all over x squared plus 4 times 3s minus 6 plus the Laplace inverse of 3 all over 3s minus 6. Now, if you observe this part of the equation, you notice that 3 is common between all of them. 3 is quite common between all of them. All right, so this can be Laplace inverse of x bar, and this is equal to the Laplace inverse of, okay, 2 all over x squared plus 4 multiplies 3x minus 6. Okay, plus the Laplace inverse. Let's do that stuff somewhere around just to save time. Now I have 3 all over 3s minus 6. Now this is equal to 3 all over 3 is common between these two. So I can factor 3 into x minus 2. Of course, 3 times s gives me 3s. 3 times 2 gives me what? 6. So from here, 3 cancels 3. That means that can be written as 1 all over s minus 2. Hence, this can be written as what? 1 over x minus 2. Therefore, it becomes Laplace inverse of 1 all over s minus 2. We have this. Alright, so if you have been following the series right from the very first video or right from the table of standard values, which is the very first video on Laplace transformation, I've said about this now. We're having the Laplace inverse of 1 all over s minus 2. Automatically becomes what? Exponential to 2. We've been explaining all of this from the very first video. So this is a table of standard value because Laplace of exponential at from the table of standard value is equal to what? Simply 1 all over s minus a from the table of standard value, where a is a number attached to the exponential sign. So which means if we are taking the Laplace inverse of 1 all over s minus a, we should be able to what? Get back this property. If we are getting the inverse, taking the inverse of this, we should be able to get back what? Exponential at. So the inverse of 1 all over x minus a, 1 over x minus 2 becomes what? Exponential 2t. In this case, it's a, so it's exponential 8t. So since here is 2, it becomes exponential 2t. So we can now fix that into that equation. So this part is solved. This part is solved. Now the Laplace inverse of x bar automatically becomes x. We already explained this in the first video. This is now equal to the Laplace inverse of 2 all over x squared plus 4 into 3s minus 6. All right, plus we'll find the Laplace inverse of this. The value is exponential 2t, so plus exponential 2t. So call this equation 1. Let's call that the first equation. So the only thing we need to solve now is what? Obtain the Laplace inverse of this. Then the solution is set and ready. So let's find the Laplace inverse of this function and plug it back into this equation. Then we have our solution. Now we have to find the Laplace inverse of 2 all over x squared plus 4 into 3x plus 6. All right, minus 6, sorry. 3x minus 6. So this is once more a compound fraction, which means we need to break this compound fraction into what? Simpler fractions called their partial fractions to be able to find the Laplace inverse. So we pick out this fraction 2 all over x squared plus 4 times x 3x minus 6. This is now equivalent to, now we have a all over, please mind you, you're having x squared plus 4. This is called repeated quadratic factor at the denominator. It's a type of partial fraction where you have, now I said in the first video when I was solving partial fractions with the use of Laplace transformation, I said that the idea of partial fraction is dependent on the nature of the denominator. Okay, we have x squared plus 4. This is called repeated quadratic roots at the denominator. Why is this so? This is simply because x squared plus 4 cannot be equal to 0. Else, you're going to have an imaginary number because x squared becomes what? Minus 4. And therefore, x becomes square root of a negative 4, which will give you an imaginary number. Hence, we have repeated quadratic factor at the denominator. So to solve this part, this is simply going to now be ax plus b. So you simply attach, as plus b. You simply now attach what? One of the factor under the denominator to what? A. So it becomes ax plus b all over what? X squared plus 4. So whenever you notice a quadratic equation of this form, this is how you solve it. Ax plus b all over x squared plus 4. All right, then plus c all over 3s minus 6. So this is simply a linear factor. In this case, you can easily equate this to 0, or it is linear because the highest power there is what? 1. So this is just x to the power of 1. All right. But because of this s squared, it is called repeated quadratic factor at the denominator. Hence, it becomes as plus b all over s squared plus 4. So you have this. So all we need to do now is to find the values of A, B, and C. Okay. All right. Now at this point, I'll have to now look for the LCM between both sides. So I'll have 2 all over x squared plus 4 times 3x minus 6. So will now be equivalent. The LCM of the right hand side still remains x squared plus 4 times 3x minus 6. Okay, so this becomes the LCM. Now the LCM divides by x squared plus 4. X squared plus 4 cancels x squared plus 4. I'm left with 3x minus 6. So 3x minus 6 multiplies as plus b. I'm going to have as plus b multiplying 3x minus 6 plus same thing. This LCM divides 3x minus 6. 3x minus 6 cancels 3x minus 6 and left with x squared plus 4. This value multiplies c becomes c times x squared plus 4. So I have this. Now, from the principle of partial fraction, since the denominators are equivalent, it means their numerators must also be equivalent. So I'll go ahead now to equate the numerators. So this is 2 equivalent to as plus b, okay, multiplying 3x minus 6 plus c into x squared plus 4. All right, so I have something like this. All right, next thing now is to expand the brackets. I'm going to have 2 is equivalent to, all right, so I'm going to now use a to expand this whole bracket first. So as multiplies 3s will be 3as all squared. Same thing, as now multiplies minus 6 will give me minus 6as. Finally, I will use plus b to also expand these brackets. Plus b times 3x will give me plus 3bs. Also, plus b times minus 6 will give me minus 6b. Next, I will expand now with c. So c times x squared will give me cs all squared plus c times 4 will give me 4c. All right, so I have this. So 2 is now equivalent to, let's bring all the terms that have x squared together, arranging them in order of what? In decreasing order of x. So I have 3a, this is 3ax squared, and I have cs squared. So bring them together. So it is 3a plus c multiplying by s all squared plus, next now we'll move on to the terms that contains x. I have 3bs here and I have minus 6as. This becomes 3b minus 6a all times s. Finally, we'll move to the constant terms. I have minus 6b, I have plus 4c. These are the constant terms, so we'll have plus 4c minus 6b. All right, so you simply have this. So the next thing to do now is compare coefficient of s on both sides of the equation. Compare the coefficient of x on both sides of the equation. On this left hand side, there is no x. So which means invisibly we have 0x squared plus 0s plus 2. That's what we have on this side. So comparing the coefficient of both x squared, x, and of course the constant term, 2 is a constant. Comparing their coefficient now, we are going to have for x squared, okay, for x squared, the coefficient on the right hand side is simply what? 3a plus c. But on the left hand side is 0. Hence, this is equal to 0. Call this equation 1. Alright. Okay, so let me pull it up here. For x squared, we have 3a plus c to be equal to 0. This is equation 1. Similarly, for s now, on the left hand side, x is also 0. Meanwhile, we have 3b plus 3b minus 6a on the right hand side. So this is 3b minus 6a is equal to 0. Call this equation 2. And finally, for the constant term, on the left hand side we have 2, and on the right hand side we have 4c minus 6b. So 4c minus 6b is equal to 2. This is equation 3. That becomes the solution. Now let's now solve these 3 equations simultaneously and find the values of a, b, and c. So from equation 1 we can make c subject to the formula in terms of a. So from 1, c is equal to what? minus 3a. Of course, if I send 3a over here, therefore c becomes minus 3a. Call this equation 4. Now, substitute equation 4 into equation 3 to obtain terms in just a and b. Substitute equation 4 into equation 3. So if we do that, this is 4c, we have 4. In place of c, c now is what? Minus 3a. Okay, minus 6b, this is equal to 2. So 4 times 3 will give us minus 12a minus 6b, which is equal to 2. Now call this equation 5. Observe now that equation 5 and equation 2 are now in terms of what? A and B. A and B. So which means I can solve the two of them simultaneously. So pull out equation 2. I have here, okay, this is 3b minus 6a, which is equal to 0. This is equation 2. Solving them simultaneously now, the best approach is to use elimination method. Let's say I want to eliminate b. If I want to eliminate b, then the coefficient of b in equation 2 is 3. The coefficient of b in equation 5 is minus 6. So I'm going to be multiplying equation 5 all through by the coefficient of b in equation 2, which is now what? 3. Then multiply equation 2 by the coefficient of b in equation 5, which is not what? Minus 6. Okay, so this will help me to eliminate. All right, so let's do this and see. 3 times minus 12 will give me minus 36a. 3 times minus 6b will give me minus 18b. Similarly, 3 times 2 here will give me 6. So this is equal to 6. Call this equation 6. Okay. Also, minus 6 times 3b will give me minus 18b. And minus 6 times minus 6a will give me plus 36a. And this is equal to minus 6 times 0. Obviously, that gives me 0. Call this equation 7. At this point, we eliminate by what? Subtraction. So subtract the two equations. If I do that, I have minus 18b minus minus 18b. Watch. Minus 18b minus, I'm having here minus 18b, minus minus 18b. So minus minus becomes plus. So this is actually minus 18b, minus minus is plus, so plus 18b. And minus 18b plus 18b is equal to 0. So I've been able to what? Eliminate b. So this is off and this is off. Now I have minus 36a minus 36a. Minus 36a minus 36a. So minus 36 minus 36, obviously, this is, let me explain this over here. So we have minus 36a minus 36a. So this is actually, this will actually give us minus 72a. All right, so we have minus 72a to now be equal to 6 minus 0 remains 6. So we can now solve for a using that relationship. All right, so from here now, we can make a subject. Therefore, a becomes what? 6 divides minus 72, which implies that, of course, 6 goes into 6 is 1, 6 goes into 72 is 12. All right, therefore, a is simply equal to what? Minus 1 all over 12. So we'll obtain a now to be minus 1 over 12. Now, if you know a to be minus 1 over 12, you can substitute into equation 4 to find what? C. All right, so if a is minus 1 over 12, let's put that into equation 4. I think I can wipe this now. I don't need it anymore. All right, so we can put that into this equation to find C. Therefore, C is equal to minus 3a, and a is minus 1 all over 12. Minus times minus becomes plus. 3 times 1 gives us 3 all over 12. So this simply implies that C itself is equal to 3 into 3 is 1, 3 into 12 is 4. You have 1 all over 4. All right, so we have C to be 1 over 4. If you know C as 1 over 4, you can put that into equation 2 to find B. Okay, you can put A into equation 2, or you can put C into equation 3 to find B, whichever. But let's go with C into equation 3. Now, in equation 3, you have 4c, which is 4, but c now is 1 all over 4 minus 6b, which is equal to 2. So 4, of course, 4 times 1 over 4 becomes 1 minus 6b equals 2. Now let's send 1 over to this side of the equation. So I have minus 6b equals 2 minus 1 minus 6b equals 2 minus 1 is 1. Therefore, you can find b to now be equal to what? 1 divided minus 6. So b is simply minus 1 all over 6. All right, so we know the values of a, b, and c. We can now plug it now into this equation. Hence, the 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 partial fraction, okay, of that compound fraction becomes, we said ax plus b, and a is minus 1 over 12, so you have minus 1 all over 12 times s plus b. B is simply minus 1 over 6, so this is actually minus 1 all over 6 all over x squared plus 4, okay, plus c over, and c is actually 1 all over 4, so plus 1 divided by 4 all over 3s minus 6, okay. All right, so the compound fraction 2 all over x squared plus 4 into 3x minus 6 have now been broken down into this. So let's look for the LCM between 12 and 6. The LCM is obviously 12. So LCM there is 12. 12 divided by 12 is 1. 1 times minus 1 times x gives us minus s. 12 divided by 6 is 2. 2 times minus 1 gives us minus 2. Okay. All over x squared plus 4 plus 4, okay, plus similarly, okay, this is simply 1 all over 4 all over. Now please watch, 3 is common between these two, so I can pull out 3. This is now 3 into s minus 2. Of course, 3 times x, 3x, 3 times 2 will give us 6, so we have this. Now this is equal to, I can now send this 12 down. It becomes minus s minus 2 all over 12 into x squared plus 4. So I have x squared plus 4. Okay, plus I can also send this 4 down. It becomes 1 all over 4 times, not forgetting there is 3 there. So 4 times 3 into s minus 2. I have this. So this compound fraction 2 all over x squared plus 4 times 3s minus 6 is equivalent to, now I can split this into 2, minus s minus 2 all over. This can now be written as minus s all over 12 into x squared plus 4, okay, minus 2 all over 12 into x squared plus 4. Okay, we can split this to be this, still the same thing as this. All right, so this is now plus 1 all over 4 times 3 gives us 12 into s minus 2. Okay, we have this. Now, of course, 2 can still go here. 2 goes here. Okay, 2 can still go there. So we have 2 all over x squared plus 4 into 3x minus 6 is now equivalent to, this is minus s all over 12 into x squared plus 4. Now 2 goes into 2 is 1, so I have minus 1 all over 2 goes into 12 is 6. 6 into x squared plus 4. Okay. Now, therefore, the Laplace inverse of 2 all over x squared plus 4 into 3x minus 6 is now obviously the Laplace inverse of the individual results. So we have Laplace inverse of minus s all over 12 into x squared plus 4, okay, minus the Laplace inverse of 2 all over 12 into x squared plus 4, okay, plus the Laplace inverse of 1 all over 12 into x minus 2. Okay, we have this. So we can simply rewrite that result. We can simply rewrite now that results for the Laplace transformation. Okay, so bring out, now this is 1 all over 12 or minus 1 over 12 is common here, so you can pull it out of the Laplace sign since it's a constant. So this is equal to minus 1 all over 12 Laplace inverse of, I have now 1 all over x squared plus 4. So this is, sorry, s all over x squared plus 4. We have this. Same thing, I can pull out 1 over 12 and still leave 2 here. Please be very careful. Still leave 2 here. You have minus 1 all over 12 Laplace inverse of 2 all over x squared plus 4. And finally, we have plus, same thing now, pull out 1 over 12. You have 1 all over 12 Laplace inverse of 1 all over, this becomes x minus 2. You have this. Okay, so let's now find the Laplace inverse of those functions. All right, so from the table of standard values, we've already done that in our videos. Do well to watch all the videos from beginning for proper understanding. Now, from the table of standard values, we said that the Laplace of cos at, the Laplace of cosine function cos at, is simply given as s all over s squared plus a all squared. So this simply means that Laplace of cos 2t, let's say now a is equal to t, a is equal to 2, this will now be equal to what? S all over what? X squared plus 2 squared, which is s all over x squared plus 4, because 2 squared is 4. So Laplace of cos 2t will simply give us s over s squared plus 4. Now, this simply means that the Laplace inverse, if I should not take the inverse of s all over x squared plus 4, I should be able to get what? Cos 2t. So the Laplace inverse of x over x squared plus 4 is cos 2t. Hence, I'm saying x over x squared plus 4. That means this is actually what? Cos 2t. This side is defined. Again, we talked about the Laplace of cosine of sine values. So Laplace of sine 80 from the table of standard values, we said this is equal to a all over x squared plus a all squared. So which means if I'm asked to find the Laplace of sine 2t, this is actually what? A is now the number, which is 2 all over x squared plus 2 squared, which is now what? 2 all over x squared plus 2 squared is what? 4. So this simply means that if I'm looking for the Laplace inverse of what? 2 over x squared plus 4, automatically it should give me what? Sine 2t. So which means this part is solved. The Laplace inverse of 2 over x squared plus 4 is simply what? Sine 2t. And finally, we said the Laplace of an exponential function, let's say exponential at, we agreed that this is equal to 1 all over s minus a. So if I'm asked to find the Laplace of exponential 2t, okay, that means this is going to be what? 1 all over s minus 2. Hence, if I'm asked to find the Laplace inverse of 1 over s minus 2, I should know automatically it will bring me back to original function, which is what? Exponential 2t. Hence, the Laplace inverse of 1 over x minus 2 is simply exponential 2t. So we can now plug them back into those equations. All right, so if we plug them back now, we are going to have that the Laplace inverse of 2 over x squared plus 4 times 3s minus 6 is now equal to, remember, minus 1 all over 12. Laplace inverse of x over x squared plus 4 is simply what? Cos 2t. So times cos 2t, okay, minus 1 over 12 again, so minus 1 all over 12. Laplace inverse of 2 all over x squared plus 4, that simply gives us what? Sine 2t over here. So this times sine 2t, okay, plus again 1 all over 12. The Laplace inverse of 1 over x minus 2 simply gives us exponential 2t, so times exponential 2t. All right, so if you rearrange that equation, of course, 1 all over 12 is common amongst all of them. If you want to, okay, you can simply now have that the Laplace inverse of 2 all over x squared plus 4 into 3x minus 6 is now equal to 1 over 12 is common amongst all, so you can simply pull out 1 all over 12 into, this is now minus cos 2t minus sine 2t plus exponential 2t. So this becomes the Laplace transformation of this, the inverse transformation of this given function. Now, having found this, we can now substitute into what? Equation 1 to find the solution of the differential equation. Therefore, the solution of that equation, x is now equal to, in place of the Laplace inverse of this function, you put this down, 1 all over 12 into minus cos 2t minus sine 2t plus exponential 2t. Finally, we have here plus exponential 2t plus exponential 2t.